Hey, good afternoon. My name is Jan Martinovic. I'm from IT for Innovation National Supercomputing Center, and I would like to welcome you on the session about future challenges in IoT, AI, and convergence of HPC cloud and big data at the Data Week 2021. Yeah, this session is co-organized with Maria Perez, full professor at the University Polytechnica de Madrid, and with Stefan Hachinger from Leibniz Supercomputing Center. The main purpose of this session is to present to you the current status in the ICT 11 projects and share between the projects challenges, future visions in the topics of Internet of Things, AI, large-scale HPC, cloud computing, and big data. Our session is divided to two parts: the public part, which will contain 5 presentations from ICT 11 projects, and then we will continue with a private session when we will discuss the future challenges between ICT 11 projects and BDVA. We will continue in the next hour with presentations from 5 ICT 11 projects. We will start with DPAD, then we will have IO Twins, Sibel, Evolve, and we will end with Lexis projects. Before we will start, I would like to ask also Maria Perez for a few words as a welcome.
Okay, so thank you. So good afternoon, everyone, and thanks to Jan and Stefan for inviting me to participate and coordinate this session. So as Jan mentioned, I am professor in Universidad Polytechnica de Madrid. I am also part of the board of directors of BDVA DAIRO, a member of the Research and Innovation Advisory Group of the HPC joint undertaking. So this is the follow-on session of other 3 ones that we celebrated before on May and July last year, and also in the HPC week this year in March, in which we analyze the perspectives, challenges, and limitations of the large-scale pilots developed in the context of the ICT 11 calls. As a result of these activities, we obtained some of the main challenges to be addressed in 4 focus areas in the HPC SPDA spectrum: data, workflows, HPC cloud infrastructure to edge, and AI. And all these topics are very relevant for BDVA DAIRO. So, well, I am looking forward to discussing with you and to hearing from you about all these interesting areas. Thank you very much, and let's have a great session. So thank you.
Thank you, Maria. And now I would like to ask the first presenter, which is Marco, to share the slides and start the presentation.
It is my turn.
Yes, please. Shall we give you 5 minutes time before end, or 3 minutes time better? Or are you okay?
Okay, I'm fine.
Good.
Let me share. So good afternoon, I'm Marco Aldinucci from University of Turin. I'm here talking for the DPAD project, one of ICT 11 project, specifically focusing on health and the usage of HPC and AI for health. Project coordinator is Monica Caballero Galote from Everest, and the scientific coordinator is John Ander from UPV Valencia. So DPAD is structured this way. We basically focusing on two main foreground products that are 2 libraries that are ADDL, the European Distributed Deep Learning Library, and the ACVL, the European Computer Vision Library, that are 2 new libraries entirely designed within the project that leverages on HPC and AI, HPC and cloud infrastructure to provide to the medical doctors and the medical setting the power of AI for analyzing, diagnosis, and personalized medicine. The project has a number of important, quite large number of pilots, because there are over 10 medical real trials that try to use the libraries and the tools we develop for validating them. I have to say about that other two words that it seems somehow strange to focus on building libraries for AIs. You may think that they exist already, they are done already, but it is important to remind that they are the crucial part of the value of a certain industry. If you think today of market leaders, as for example, NVIDIA, that is one of the market leader in hardware for AI, they basically build their leadership on the library, not only on the hardware. So most of our colleagues use NVIDIA hardware because of cuDNN, not because there doesn't exist any other hardware. So DPAD focus on that and try to develop a European value on that and make it at the service of an important area, important vertical, that is health. One of these two libraries recently received, in just a few months ago, the European Innovation Radar Award, that in particular there has been three partners of the project has been awarded. That was Everest, Spain, University of Reggio Emilia, and University of Turin, my university. There are some challenges and with respect to this particular area, and with respect to data in particular, medical data is not as other data, is very, very difficult to manage because they are critical. We need to preserve privacy, and this is particularly difficult when coupled with the need to be fast and to make it high performance, and do it by using shared infrastructure as our supercomputer. It's equally difficult to set up a workflow that put together the tools that are typical of HPC, that are queue, batch execution, and the need of AI applications that are not batch execution, but is much more interactive, and notebook and stuff like that. So there are two clear challenges, and the project tried to address them by developing a specific foreground value for both finding way of having multi-tenancy in the area of HPC and cloud, and developing specific workflow product for executing high-performance AI application on shared infrastructure, hybrid, HPC, and cloud. This is not, there are other challenges that indeed using the whole portfolio or HPC solution, including GPUs and FPGAs and other, let me say, specialized hardware. We all know that the scenario in the hardware evolution is going towards specialization. So we are trying to do what all we do by keeping in mind that our solution should be portable on a heterogeneous platform, and in the end also having good accuracy and good result from our library and approach that is last but not least. So having good result from the diagnosis and the use case we take care. So I see that the time is running, and let me go fast. In the project, we are exploiting several infrastructure. Among those, the Barcelona Supercomputing Center, our own at the University of Turin center that is specifically designed for exploiting AI on HPC and AI tool, and also a specialized machine like experimental FPGA cluster at UPV. And from the viewpoint of, let me say, system software or software that enable the usage of the library we are developing, we are exploiting two main products. One is developed at Barcelona, is the COMPS task-based framework that we use basically to accelerate the training, so transforming our library into distributed training library. And another one that is so-called StreamFlow, that is more workflow manager system that is developed at University of Turin, that is act as a glue for putting together HPC cloud and provide the power of HPC to the user that would like to use notebook and not HPC tool, and do it by keeping in mind that data is critical, cannot be easily shared, should be under control, should be segregated in the shared system, and all the other constraints that are typical of medical data. I didn't talk too much about the pilot there. I didn't prepare a slide for that, but I quickly can say that there are over 10 important pilots, most of them in the area of analyzing medical images or medical data. Most of them are on cancer of various types, and in which we are getting extremely good result. Among those, we published a paper on Lancet, on the Lancet journal, this January. I myself one of the author, and in which we succeeded to guess stroke with an accuracy that is over 90%. So over 9 times over 10, we guess stroke in a 1 year time frame. And that is, I think I respected the timing.
Thank you, Marco. And before we will move to the next presentation, I would like to only mention that you all the people who are listening have a possibility to use VOVA platform for asking our speakers questions. If we will have time, we will select a few at the end, or the speakers will directly answer to your questions by the VOVA. So not hesitate to ask a question. So now, thank you, Marco, again, and Paolo. Now it's time for IO Twins presentation.
Thank you for the introduction, Jan, and thank you to all of you for organizing this session. You should be able to see my screen now. And yes. Yeah, very rapidly, given the time constraints, I'm Paolo Bellavista from the University of Bologna in Italy, and I'm presenting here some research results that we have already obtained within the framework of the IO Twins project. This is the fish about the project. Basically, and very rapidly, there is an industry that coordinates the project that is called Bonfiglioli Riduttori, and the University of Bologna with me manage the scientific coordination of the project. To summarize very rapidly the approach that we have in the IO Twins project, basically the original element of the IO Twins project is to try to put together an ICT infrastructure in order to reduce the barriers to adopt a specific approach for industrial big data projects that we call based on distributed and hybrid digital twins. In the next slide, I will show to you why distributed and why hybrid. but also in comparison with what Marco has already presented to you, one specific original aspect is that in the IoTwins project, we concentrate also on the execution of this digital twin on edge cloud resources in the proximity of the data sources for a series of motivation. Our digital twins are hybrid and distributed. In which sense? Well, hybrid because they are digital twins that exploit different kinds of models, fully data-driven sometimes, but also data-driven through the generation of synthetic data via physical simulation on the cloud or on HPC resources, and agent-based simulation as well on cloud or HPC resources. This is the idea of hybrid. The idea of distributed is that once we have trained our digital twins, the digital twins can decide to execute in a distributed way, typically by having the first initial training phase on the cloud and HPC, and then the so-called control phase over edge nodes in the proximity of data sources, so to be able, for example, to reduce a lot the latency of control loops towards industrial processes, and to increase, to say in one single word, the data sovereignty and the data control of the data generated by the industrial plants that we are managing. So, for example, in this other figure, you can see step by step that we are able to have a distributed edge twin part of the digital twin that is able to work in the proximity of the data sources, to have controls, for example, over the industrial test beds with reduced latency, increased reliability, and with the possibility to go in refinement of the trained model locally in enabling technologies such as federated learning on single industrial plants or test beds. This is the basic idea and the unifying kind of methodology that we are applying over all the 12 IoTwins test beds. We are at the beginning of the second half of the project, and the main results that we have already delivered are the so-called IoTwins framework, that is the putting together of a methodology for designing our distributed and hybrid digital twins in different verticals, and a reference architecture through which we are able to put together different requirements, but also different components of the infrastructure that can derive from legacy constraints of the test beds we have to face, and two sets of originally developed components, one set non-AI related service components, for example, for orchestration in this kind of scenarios, the other AI related service components, typically for anomaly detection and analysis of time series or optimization of tuning parameters. This is done.
Paolo, 1 second, you have 4 minutes left.
Okay. These are mainly the results. They are put into a common and unique reference architecture that is able to be incarnated in different kind of realization depending on the service component that are legacy for each test bed. And so we are able to propose a common approach in very differentiated test beds, for example, 4 about industrial manufacturing and 3 about facility management. Last point, we are replicating some of these test beds within other test beds that differentiate from the first based on the scale, in order to verify and evaluate the replicability of the approach. In the slides, you have some short description of some testbeds that are particularly central to the project, but this is material left just for the attendance in order to get additional information about the project. I will spend the last 2 minutes to say that in terms of challenges that we have already investigated and that we have identified in the field, for sure, for the IoTwins project, a crucial point is to be able to support the so-called distributed cloud continuum. So for us, the distributed cloud continuum has a crucial point in the edge cloud, and in particular over the edge, that is industrial gateways for us, but also 5G edge nodes. The crucial point is to be able to support distributed machine learning for the kind of artificial intelligence oriented, big data driven analysis that we do. What we see as very open is how to put this together with dynamic deployment that takes into consideration guaranteed or managed quality of service, especially for the Industry 4.0 or in a few months 5.0 domain, in which the control loops require to have given degrees of reliability and of latency that are, let me say, managed by the infrastructure. Final point is about the emergence of an ecosystem that simplifies to small companies to participate in this kind of scenarios, because sometimes the data sets that can be put by a single company are not sufficient to make significant results, to extract significant added value information from raw measurements and raw monitoring data. So putting together a platform that simplifies and reduces the barriers to enter this kind of innovation ecosystem, but also business ecosystem, is crucial for us. And yeah, there is also one slide about specific role of HPC resources in this kind of scenario, but I believe I can skip it so to be perfectly in time.
Thank you, Paolo. And the next speaker will be from Sibel Project, Sofia Karagiorgu. So, Sofia.
Good afternoon from my side.
We can see your screen.
Thank you, Jan. Thank you all. I'm Sofia Karagiorgu, head of AI at UBTech and adjunct lecturer at the Harokopion University of Athens. I'm the technical coordinator of Sibel, a project dealing with big data, AI, and HPC, and targeting the agri-food domain. Sibel is envisioned to convergence HPC, big data, and AI technologies, coupled with numerous and diverse pilots. So focusing at several fronts regarding task parallelization and execution speed up for organic soya yield prediction, hyperparameter tuning adapted for Spark regarding food safety, aquaculture monitoring and feed optimization, distributed execution over Spark and big data partitions having multi-workers and multi-executors for crop yield forecasting and OpenSea fishing applications, usage of multi-nodes and multi-GPUs for autonomous systems with Arable frameworks, big weighing optimization and sustainable big production, and task parallelization over HPC for climate services. Some core Sibel solutions include the provisioning of layers and services such as the resource abstraction layer, which leverages and efficiently orchestrates both HPC and data partitions in a transparent to the end user way, seamless HPC, big data and AI resource management over diverse frameworks, underlying frameworks and stacks, including systems and testbeds through a tool, the experiment composition environment tool, which eases the design, composition and enactment of AI applications at the diverse workloads, meaning HPC or big data, but also optimal time partitioning and scheduling, which identifies idle slots among the executions of HPC and big data in order to collocate more tasks to be executed. Conceptualizing the solution of Sibel resolves around different layers, including data services layers to onboard data, perform data curation, cleaning, semantic alignment, encryption, and anonymization. Having the advanced query builder to perform distributed queries over distributed storage systems, the visualization and reporting layer to expose the result in a user-friendly manner, the experiment composition layer which integrates in a containerized images, machine learning and deep learning models for the actuation of the applications, the parallel and distributed execution management layer, which abstracts the resources of big data HPC to the end user, supporting the co-location of idle slots, a data and infrastructure security layer supporting security by design for the entire platform, but also a dashboard which exposes all these services in a user-friendly way to the agri-domain users, which can exploit historical and real-time data and maybe data scientists, research community, agri-consultants, or food growers coming directly from the domain itself. How we materialize contributions of Sibel in the European HPCDA space, this is realized by means of a collection of data services for harvesting huge amounts of images, time series, textual data, services for provisioning and a transparent HPC big data infrastructure with parallel and distributed capabilities, public Docker registries and repos for machine learning, deep learning models to be easily used, onboarded, and deployed, resource abstraction mechanisms translating application level configuration directly to the real sources and bare metal requirements, but also new products and innovation in the field of precision agriculture and precision livestock farming, including food recalls, prediction and safety, saving time in data-hungry and computationally intensive simulations, but also robust models and with higher accuracy and resources preservation. Sibel has been inspired by diverse, let's say, fronts, including societal, tech, and agri-domain requirements. And therefore, huge data volumes are being collected for geographically distributed areas, novel added value services for food safety, resources preservation, weather predictions, better and more food are currently developed, but also from the need for global and local learning preserving privacy and contributions towards advanced decision-making algorithm, but also last but not least, the need for distributed processing and speed up of very time-demanding processing tasks. How we are positioned as a team in the fields that we are prioritizing our effort in the direction of AI. It incorporates edge and distributed parallel machine learning algorithms, big data, HPC, and cloud infrastructure by distributed and parallelizing tasks according to the business needs and requirements. In the direction of data regarding the veracity of the models and the analysis from the agri domain, which is translated into applications and digital transformation. But also dynamic workflows, which are supported by on-demand resources allocation and application enactment in the support of distributed analytics directly coming from the domain. Thank you. This brings me to the end of my presentation, and the floor is yours, Jan.
Thank you, Sofia. The next presentation will be from Evolve Projects, presented by Angelos Bilas. So yeah, we can see your screen. Perfect.
All right. Good afternoon, everybody. I hope you can hear and see me as well. Thank you, Jan, for this opportunity to present Evolve and what we've been doing over the last 2.5 years. My name is Angelos Bilas. I'm with Forth, and I've been the scientific director of Evolve since its conception. So Evolve is a project at the crossroads of big data, cloud, and HPC. The goal and scope of Evolve has been to process large data sets and do so interactively for user-facing applications. So if I am to summarize the main achievement of each of these worlds, right, over the past several years, many years, right, I would say that big data is all about productivity. Basically, big data frameworks have managed to decouple platforms from users from platforms, and they allow users to process large amounts of data with a few lines of code. This was not possible before. The cloud has been mostly about optimizing resource cost. It has driven consolidation, resource provisioning, shared use of resources, and today dominates. It's used extensively for managing available resources. And HPC has always been about efficiency, squeezing every cycle out of the tasks we need to execute, and doing so with vertical integration and by using customized architectures for storage, interconnects, and accelerators. So how does Evolve bring these three worlds together? First, Evolve proposes, puts forward a heterogeneous hardware platform. This is the figure on the left. This is a hardware platform designed by Atos and DDN. On the right, you can see a figure with some of the characteristics in the platform. The platform has different types of processing, host CPUs, different generations of GPUs, FPGAs for acceleration. Servers use large memories, and there is multiple and different interconnects in the system, as well as different types of storage technologies, including SSDs, NVM, and high-capacity magnetic disks. On top of this platform, Evolve builds its software stack, which for simplicity to the users looks like as a dashboard when they connect to the system. So the dashboard is the front end for all users. It offers secure and private user management via isolated namespaces. It provides notebooks as a main abstraction. So users see notebooks and they can execute or write their code in notebooks, both via templates and in a programmatic manner. The dashboard integrates Evolve services with several other third-party services that are essential to support workflows, and everything is integrated over containers, as I will discuss next. And the dashboard has taken significant integration effort to get to a point where it is actually useful for users and use cases in the project. Now, Evolve, for productivity purposes, uses workflows as a main abstraction. Workflows for us, essentially, they are end-to-end synthetic descriptions of computation. Workflows are important for two reasons. The first reason is that users care about workflows more than individual tasks, right, or individual steps of the computation. Workflows describe an end-to-end process, right, and therefore include intermediate data movement and anything that needs to happen to get the job done. And also, workflows are important because they basically leave more room for the system to optimize execution. So figuratively, a workflow in Evolve would look something like what you see on the slide here. Maybe so first you open a data set, then you use Spark to clean up the data, then you use TensorFlow to train, right, the data set. Then after that, you may use MPI to simulate something using data and parameters from previous steps. And in the end, you post-process the data and you visualize them for inspection purposes. Now, one particular aspect of Evolve is that it integrates in workflows both HPC and big data frameworks, computations, as HPC tasks as computation. So workflows can include and execute MPI code. MPI stages can also be invoked interactively from notebooks. MPI tasks make use of GPUs and Infinite GPU and accelerator and InfiniBand support from within containers. And behind the scenes, Evolve takes care all of the machinery required, right, to execute tasks and stages of workflows concurrently on the platform. Now, for resource efficiency, Evolve includes an elaborate runtime system. The runtime system at a high level is built on a set of microservices. These microservices are basically frameworks coming from the HPC and the big data world. And these are necessary, these are broadly used frameworks that people today use to write workflows, so they are an essential part of the platform. Everything is integrated to top of containers and under Kubernetes. Specifically for HPC tasks, Evolve allows Slarm to run collaboratively as a slave under Kubernetes, and they do collaborative resource allocation. So HPC jobs can run unmodified as a stage of an Evolve workflow. There is a lot more attention with respect to resource allocation and resource assignment, but I will not go in more detail into these aspects of the project. Right, thank you. One last element with respect to the runtime. Evolve includes a unified storage layer, and this layer essentially abstracts data and creates a notion of data sets. So workflows and data sets are able to use data set names to process data without the need to worry about where data is located or what device technology is used to store data and how to access them. All this happens transparently right under the unified storage layer. Now, to test the technology and verify the validity of the technologies within the project, Evolve uses use cases from multiple domains. So it includes 7 use cases pilots from automotive, mobility, earth observation, and public transportation. And in addition, it includes 15 proofs of concept. These are, let's say, smaller use cases that have been used to guide and validate ideas in the project. If you're interested in trying out the Evolve platform, please get in touch. People will be more than happy to sit down and discuss with you and see what makes sense, right, for your case and your application. Now, last, I'd like to share a few thoughts that we have had and we have been discussing about extending what Evolve does and computation towards the edge. So Evolve is mainly about processing in the data center. And the main question, right, that is still open is, where would we place even more processing? And the reason for more processing is because data grow at a very fast pace. So we could think of about building larger data centers and building more data centers, right? But all these approaches are essentially in the end limited by power or by latency. Therefore, using the edge in the end is our silver bullet for increasing processing capacity and reducing response latency. So for us, the ideal, let's say, edge would be transparent to use for productivity purposes, and workflows are a great abstraction for this. However, there is a lot to be done and a lot to be said about workflows before they become mainstream. They are not a fully mastered art yet, right? Second, the edge should help us increase processing efficiency and density. And there is a lot we can do with parallelism and acceleration. There is a lot of opportunity. However, this opportunity is very difficult to harness. For instance, if you try to add a new accelerator under TensorFlow, there is a lot that needs to be done, right? A lot of work. Third, the edge should help us reduce decision latency by distributing state and data close to the source. However, this is a different type of distribution from what we've been doing within and across data centers, right? And generally, state distribution and managing distributed state has been a hard problem over the years. Fourth, the edge should help us achieve and should deal with interoperability and isolation, especially in the presence of multiple administrative domains. And in the edge, we will have to deal with multiple administrative domains because there is many, right, different entities that have to use the edge and they have to be involved with data at the edge. There is a lot to be done, but it looks like a very exciting decade going forward. And with this, I would like to thank you for your attention, and I'll be happy to answer questions via email. Jan, the floor is back to you again.
Thank you, Angelos, for a very nice presentation. And now we will go to the last part, and it will be presentation of the Lexis project provided by Stefan Hachinger. So Stefan, you can share your presentation with us. Yeah, okay, we can see it. But we cannot hear you.
Now you can hear me, right?
Yeah, now we can
Perfect.
hear you.
Sorry, guys. So hello, everybody again. And I would last but not least like to present Lexis on, and I've called my presentation Orchestration and Data Management in a Convergent World of HPC, Cloud, and Big Data. So I'm very happy to speak for the entire project here. And I myself, I'm leading the data system part. So it relates also to the data topic. First of all, I would like to introduce to you some key points of the Lexis platform. That is what it's about, basically, right? So on the one hand, we have the orchestration topic. We want to orchestrate complex workflows which run on cloud HPC big data systems, and they treat big data. And actually, this is a geo-federation. So we are working on multiple computer centers here, as you will see in a few moments. And the orchestrator handling all these systems is basically called York, and it's based on Tosca language. But we have a GUI, so the Alien for Cloud GUI, which helps the users to develop actually the workflows without programming directly. And to address the HPC systems, we have the HIPI middleware. So thus we can construct real-time workflows, we can construct urgent computing workflows as well. So we have a few challenging use cases. On the data side, we are relying on EUDAT services, and we've built a cross-site data federation within Lexis, which can connect to other EUDAT systems. And that's based basically on the integrated rule-oriented data system, which you see here in the middle. It's called IRODS. And then data transfers can also be accelerated in the project by, for example, burst buffer systems, and can be reprocessed FPGAs and GPUs. So all this is nice and good, but you need to give a good accessibility to the user. So we have a portal where you can actually start these workflows and set up the input data, retrieve the output data, and such things. And all this provides you also with a single sign-on, because we have a key-cloak-based AAI solution. And last but not least, the fourth characteristics of the project, which is very important, are the stakeholders, which basically are mixed from industry and science. And so we follow the paradigm that big data should be for everyone, HPC should be for everyone as a service, and everyone should be able to access it with a nice way. And for industry usage, we have also taken care of an accounting and billing concept, which is implemented with the Cyclops software. So all in all, you put the workflow and data in our platform, and then they are executed on HPC clusters and cloud systems. That's a graphic which basically summarizes our concept. The pilot use cases are from aeronautics, so CFD and gearbox simulations, which should be accelerated and live monitored within this project. Then earthquake and tsunami simulations, where we have predictive models, and they are executed in an urgent computing manner. And last but not least, weather and climate pilot, where we have various HPC simulations, which then feed smaller simulations on the cloud, post-processors for flood simulation, wildfire, agriculture simulation, and that's got a whole wealth of applications. All that is run on that infrastructure, which you see here. It is basically just for you to have a view on what we've built. You don't have to understand the details, but you see here the cloud parts, for example, an LRC, ID4I. Here is now a next center included is iTech in Ireland. And that means basically we are also ready to include further centers in the federation. We are providing then the software stack in the end of the project and have open software. And they are all coupled with this data layer down here. So DDI, distributed data infrastructure, which I give you a glimpse now. So basically this is a federation of 2 servers and now to be 3 servers also at iCheck, where this IROT system basically gives you a file system on a file system. So we have a unified view on the Lexis data, which are lying on the LRZ and ID4I and iCheck backends, but they are transparently fetched whenever needed to the other center, because this IROT federation works with transparent data transfers. Also, it can be told to mirror data automatically. So integrated rule-oriented data system means you can make rules and policies for your data handling. And then we have a staging API, so a REST API to basically stage data to cloud and HPC systems that we use. So there you can give the command, please stage me this data, and then it will be executed in background. And that's also our entire concept, basically. So the DDI integrates into the rest of the Lexis world with some APIs. So data search API, where you can do data discovery, search for metadata and data. Then a staging API and some other APIs which are not depicted here. And all of this under the hood of a common authorization and authentication infrastructure. In the EU.dat world, it integrates basically by using the EU.services. So it means it keeps some compatibility with this EU.dat research data service, which is also part of the European Open Science Cloud. The EU.dat has a wealth of services, which we actually picked 3 services in particular. So the B2Safe is an IROTS plugin, which makes us enabled to do policy-based data mirroring. The B2Handle provides us persistent identifiers, and that's a prerequisite for fair data handling. So findable, accessible, interoperable, reusable, which is a great fashion in research in particular. And in the end, B2Stage enables us to do data staging to the HPC systems in particular. We will try to export our data to B2Find, which is a metadata aggregator. So basically a search portal for research data. So first real runs have been conducted and have been presented at the SC20 conference. So we have a weather workflow, which then feeds basically a forest fire prevention model. And we successfully run this and then presented it. You can have a look at the post under this address if you're interested. And the staging API and the VCDA were basically used to automatically control the data movement within this workflow. And now we're going on to validate the platform further. And for this, besides our 3 pilots, we have so-called open call users. So we've issued a call for everyone who wants to try out this platform. You can find it on our webpage and you can participate, of course. And it means basically you can use our resources, of course, a certain bunch of our resources for free, and will in turn provide us feedback on our platform. And by this, we widen the workflow range even more. On the other hand, we do some internal benchmarking, of course, point-to-point transfer tests and so on, in order to find bottlenecks. And that's the stage at which we are currently basically at. So we're finishing up the technical platform and then eliminating the bottlenecks. To take home some strategy items, I've created this slide. And it gives you some key points, which I already mentioned. So we do basically infrastructure, which enables big data. Yeah? So we are the infrastructure experts, I would say, and we set up this distributed orchestration with a distributed data backend. And that combination is basically the unique thing, so that we try to optimize and also automatize the data flows in the back, and then try to optimize the whole workflow process, and that all using European software and basing it on EUDAT. And of course, as much as possible, open source components and so on. Direction of all this is that we want to make cloud and HPC converge, but also the academic and industrial usage patterns, which are sometimes very different. And by our mix of users, we provide a solution which can be used by both, basically. And we try to align this also with the SRIA of the BDVA. Here we address basically these tech priorities, data management and data processing architectures. And you will also see this further in our book chapter, which is in print. Horizontal and vertical concerns are also addressed: cloud and HPC, data sharing platforms, and cybersecurity and trust. And with this, I would like to close. And thank you very much for your attention. Here are our contacts if you need them.
Thank you, Stefan. And I would like to thanks to all presenters. We are at the end of the public session. Maybe I would like to ask if you can, for a few seconds, enable the cameras. Yeah. And Stefan, you can switch off screen sharing.
Yes.
Yeah. So thank you to all, and we are. Yeah, pardon. Yeah, thank you to all, and we will continue in this discussion in the private session in 9 minutes. So thank you again to our presenters, and see you in a few minutes. Thank you. Bye bye.
Thanks very much. Any questions, please, in the chat?
No. We are without.
Or in the HUA. Yeah. But
no, we are without questions.
We are without, yeah.
Yeah. So but not hesitate if somebody would like to ask the projects, you can contact the presenters and ask directly anything about the project which was presented.